Hello and welcome. Today we're looking at Organic Chemistry 1, review number B1, presented to you by Science Visualized. Question 1. Which one of the following statements is correct? A. Atoms lose electrons to form hydrogen bonds. That is wrong because when atoms lose electrons, they form ions. They actually form positively charged ions because the number of electrons is going to be less than the number of protons. Atoms lose electrons to form negative ions. That's wrong because when atoms lose electrons, they end up with a net positive charge. Number of valence electrons always equals to the charge formed by the atom. That is not really correct. That's only correct in group number 1A. So 1A has a charge of +1, 2A +2, 3A +3, and then group number 4 doesn't form charges. It will prefer to form covalent bonds. And then when you go to group number 5A, then the charge there becomes -3, and then number 6A becomes -2. Number 7A, like chlorine, bromine, becomes -1. And then group number 8A are inert gases like helium. They don't have a charge. So that is not correct. Group 4 atoms prefer to form covalent bonds instead of losing or gaining electrons. That's true because group 4, as we saw here, will be something like carbon and silicon, and they will prefer to share electrons. And that's why organic compounds are mostly covalent bonds because they contain carbon. So that's the right answer. Now question number 3 says circle all the structures that contain at least one sp2. Remember, sp2 must have a double bond. So all the structures that have sp2 carbon. So when you look here, there is no double bond, so no sp2. Here, that carbon will be sp2, same with that oxygen, sp2. So we circle that because we're only looking at carbon. So all these carbons here, sp3, all these carbons here, sp3. Here, this triple bond is going to be sp. So we see that only B satisfies that condition. Number 4, predict the direction as FW for forward or RS for reverse for the reactions with the following values. Now the first reaction has the equilibrium constant less than 1. Remember, the equilibrium constant equals to the concentration of the products divided by the concentration of the reactants. So if the value of the product and the reactant is the same, then KEQ will be equals to 1. If the product is 10 times more than the reactant, then the KEQ will be equals to 10. If the reactant is 10 times more than the product, then the KEQ will be equals to 1/10, which is 0.1. Now looking at this first one, the KEQ is less than 1, so that means the denominator here is much bigger, so you have more reactant, and therefore the reaction favors backward reaction, so that's going to be reverse reaction favored. Number 2, delta G is greater than 1. Now delta G is the change in Gibbs free energy. When the value of delta G is positive, we say that reaction is non-spontaneous. And therefore that reaction will require energy for it to move forward. If the value of delta G is negative, then we say that's a spontaneous reaction, and it will occur without the need of external energy to drive the reaction. So here we see that delta G is greater than 1. That means it's positive, and therefore that reaction is non-spontaneous, and it means that reverse reaction will be favored. The only way you'll favor the forward reaction there is to apply external energy. A better way to frame this question will be delta G naught greater than 0 or less than 0, and then decide whether that reaction is spontaneous or non-spontaneous. Now delta G is change in Gibbs free energy, but when you add that naught, that 0 there, that naught, it means under standard conditions. So that's under standard temperature and pressure, which basically means 0 degrees C, which is actually 273.15 Kelvin, and the pressure will be 1 atmosphere. Question number 5. Use A for acid, B for base, and then Ca for conjugate acid, and Cb for conjugate base for the following equation. What you're having here is what we call Bronsted definition. Bronsted, sometimes called Bronsted-Lowry definition of acid and base. And that basically says that an acid will donate protons, a base will accept protons or hydrogen ions. So what you need to do is just see what's happening to this reaction. Here we're starting with OH minus, and that one is changing to water, and basically that water means HOH, and you can see that we have added one hydrogen, and therefore because we are adding a hydrogen to that, it means that what we are starting here is a base, so that will be the base, and then it accepts proton to give you water, and always a base will accept proton and then it will become a conjugate acid. So water in this case will be the conjugate acid. On the other hand, an acid will lose a proton, so minus H plus, and then it will give you a conjugate base. So in this case, if you look at this structure here, it has an OH here, and here you have O minus. That means you have lost a proton. And because of that, this will be the acid, and then it loses a proton to give you a conjugate base. So we see that the answers are base for that, acid, conjugate base, and conjugate acid. Question number 6, draw resonance structures. Anytime you ask for resonance structures, remember to use that arrow that faces both sides, and that shows resonance. And always you start from a region of high electron concentration, move into a region of low electron concentration. And if you look at this structure, this carbon here has a positive charge, and therefore it will be electron poor, and therefore that has low electron concentration, while this alkene has a double bond, and therefore it has higher electron density or electron concentration, and therefore we're going to start from the alkene moving to the positive charge. And because we're moving 2 electrons, we'll use a full-headed arrow, so like that. And when that moves, you're going to get a double bond between these 2 carbons, and the positive charge will be neutralized. So remember, we use a resonance arrow, and then we redraw that structure. And now we move the double bond here, and that leaves this carbon empty, and therefore that becomes a positive charge. So because it's electron poor, the positive charge has moved to that carbon. We can draw another resonance structure again by moving these 2 electrons that form the double bond to that carbon, and you end up generating a new resonance structure. Remember, we use the resonance arrow. Then I'm going to draw the backbone. Remember, the first double bond moved there, and now the second double bond has moved here, and that has left this other carbon electron poor, and therefore it will be a carbocation, have a positive charge. And those are the 3 resonance structures. Question number 7. What are the hybridization? Anytime you see hybridization, you need to think about sp has 1 triple bond, sp2 has a double bond, and sp3 has a single bond. So what's the hybridization of the 4 carbons? If you look at carbon number A, that's this carbon, it does not have any double bond or triple bond, and therefore it's going to be an sp3 carbon. B, if you look at this carbon number B, has a double bond, and therefore that will be an sp2 carbon. C, if you look at carbon number C, that one there, has a double bond, and therefore it's also an sp2 carbon. And while we are still at this structure, this carbon will also be sp2. This oxygen, because it has a double bond, will also be sp2. That will be sp3 because it has all single bonds. Question number 8. Convert the following to a skeletal structure. Now, in order to draw a skeletal structure, you need to follow the following rules. Number 1, each corner is a carbon. Number 2, do not show hydrogen connected to carbon. Number 3, show hydrogen on heteroatoms, so that's like on nitrogen, oxygen, sulfur. And then, of course, if you have a double bond, you show it, or a triple bond. Applying this rule, we're going to label the carbons. That's 1, 2, 3, 4, 5, and 6. We see that carbon number 1 is connected to carbon number 2, so 1 to 2. And then number 2 is connected to carbon number 3. Then number 3 is connected to carbon number 4. And number 4 is connected back to carbon number 2. Number 4 is also connected to carbon number 5. And number 5 is connected to carbon number 6. Remember, we don't show any hydrogen that's connected to carbon. And here we don't have any heteroatom, no nitrogen, oxygen, or sulfur. So that's carbon number 1, number 2, number 3, number 4, number 5, and number 6. And that will be the skeletal structure. Question number 9. Use La for Lewis acids. Lewis bases are electron pair donors, while Lewis acids are electron pair acceptor. If you look at the first structure here, you have boron. Boron is in group 3A. That means it has 3 electrons on the outer energy level. Now, if you look at the Lewis structure, you have boron connected to hydrogen, connected to hydrogen, connected to hydrogen. Each hydrogen contributes 1 electron. Let me use a different color for that, for the hydrogen electron. If you count the number of electrons around boron, we're going to have 2, 2, and 2. That gives you a total of 6 electrons. But you know that for a stable structure, you need an octet number of electrons. That's called octet rule, which requires 8 electrons. But this one has 6, and therefore, because of that, it's missing 2 electrons to make 8 electrons. And because of that, we say this boron has what we call a hole. That means it has room that can accommodate 2 more electrons. And therefore, it's going to accept 2 electrons from an electron pair donor, and we know electron pair donor is a Lewis base, and because it's going to accept electrons, then that's a Lewis acid. Next, we have nitrogen. So that's an amine, but that nitrogen has 2 electron pairs, and it's going to donate those 2 electron pairs, and because it donates 2 electron pairs, that will be a Lewis base. Next, we have iron 2 chloride, and this is a transition metal, so I'll say Tm, and transition metals can accommodate more electrons. They make what's called an expanded octet. That means they can accommodate more than 8 electrons, and because of that, they will easily accept electron pair, and therefore transition metal salts are generally Lewis acids. Question number 10. Calculate a formal charge on nitrogen, nitrogen being the central atom in this structure here. There are various methods that you can use to calculate a formal charge. The easiest one is formal charge equals to valence electrons, that means the number of valence electrons of that atom on the periodic table. Because nitrogen is in group 5a, then we expect it to have 5 electrons. So valence electrons minus the number of electrons present in this structure around nitrogen. So in this case, we have here 1, 2, 3, 4, and then for each covalent bond, we count 1 electron. So another 1 and 1. So the total is going to be 1. So 1, 2, 3, 4, 5, and 6. Therefore, this nitrogen has 6 electrons, so minus 6. And that gives you minus 1. Therefore, this nitrogen has a formal charge of minus 1. Question number 11. Draw the mechanism. Mechanism shows step-by-step transformation from the starting material to the product. So draw the mechanism of the reaction below. So in this reaction, we're starting with an alkene and then reacting that with hydrogen halide, in this case hydrogen chloride, HCl, and we end up adding the hydrogen and the halogen across the double bond, and then we lose the double bond. So that's an addition reaction where you add HCl across the double bond. The mechanism for this reaction is the polar reaction mechanism. Polar reaction mechanism has 2 steps. So step number 1, you start with the alkene shown plus HCl, and then polar reaction involves, so that polar involves the movement of 2 electrons, and because of that we use a full-headed arrow. That means a double-headed arrow. So the alkene is going to be the nucleophile. That means it has higher electron density. And then this hydrogen of the HCl will be the electrophile. So you always start from the nucleophile going to the electrophile. So from the alkene to that hydrogen, and remember we're using a full-headed arrow, and then at the same time we break the HCl bond. And that will give us, you still have that structure, but now you have used the electrons to form a bond with hydrogen, and that will leave this other carbon electron poor, and that will be called a carbocation intermediate. And then plus this chlorine leaves, you get Cl minus. Now this carbocation has 1 alkyl group, 2 alkyl groups. It has 2 alkyl groups, so that will be secondary carbocation. Generally, the stability of carbocations are tertiary carbocation are more stable than secondary, which are much more stable than primary, which of course much more stable than methyl carbocation. The reason for that is because tertiary carbocations has 3 alkyl groups donating electrons by hyperconjugation, which ends up stabilizing the carbocation. Secondary carbocations has 2 alkyl groups that help stabilizing by hyperconjugation. Primary carbocation has 1 alkyl group, and then of course CH3 does not have any alkyl group. Now we finish step number 1. Next we go to step 2. And now we use this carbocation and the Cl minus for step number 2. So I'm going to copy those here. We have hydrogen there, and that's a carbocation, then plus Cl minus. And now the Cl minus becomes a nucleophile for the second step, and the carbocation is the electrophile. So the nucleophile will attack the positively charged carbon, the carbocation, and the end result will be and now you have the chlorine connected to that carbon. Now, one thing to note here is that carbocations are flat or planar. And that means if you have this as a carbocation, and then you have a nucleophile coming in, so in this case chlorine, this chlorine can add from the top. There's a hydrogen here that we're not showing now, and that will end up giving you, if the chlorine adds from the top, you end up now with the chlorine coming out like that and the hydrogen going in, plus the second product where the chloride nucleophile now adds from the bottom to the carbocation, and therefore you end up with the chlorine going in and the hydrogen coming out. Question number 12. It says, sketch or draw an energy reaction diagram of the starting material B. So we have B. We're starting with B, going to a less stable product D. Now, look at that. The energy of the product D is less stable, meaning D has higher energy than the starting material. So if you have B here, then D has to be up in energy like that. For a reaction diagram, you draw it like that, and then here you put reaction, progress, or coordinate, which could be time or different ways that you monitor or measure the reaction. And then here you're going to have energy. Most of the time it's going to be delta G, but sometimes you could also use other energy like enthalpy. So remember, higher energy is less stable, lower energy is more stable. It's just like somebody who is on the higher floor of a building is less stable. If there's an earthquake, that person will fall all the way down and lose all that energy. He will get hurt more than somebody who is outside on the ground, because that person has lower energy. So the same thing applies to chemical reactions. Now we are starting with B, which is less stable than the product D. So that means if B is here, then the product D will be somewhere there. Then that energy difference, delta G, is going to be greater. It will be greater than 0. So it's less stable. If it was a more stable product, then you end up with a product below the starting material. So going to a less stable product D, clearly showing the reactant B, which we have it here, the activation energy E act, the transition state T, the intermediate M, and the product D. So we have one intermediate. For all reactions, you will not just go from starting material to product. You always have to provide the initial energy, the minimum amount of energy required to start the reaction, and that's called the activation energy. So you feed this with a certain amount of energy, just the right amount to get the reaction started, and then that will continue to give you an intermediate, and then that will go through a secondary transition state, and then that will go all the way back to give you the product. So the highest point here is going to be the first transition state. So here they say use T for that. And then we have intermediate M, so that minima will be M, the intermediate. And then of course this will be the second transition state. And that will be how the energy diagram for that will look like. Question 13. Write a free radical reaction mechanism. Here we're told it's a free radical reaction mechanism, but actually you don't even have to be told that. Anytime you see an alkane, like in this case ethane, reacting with a halogen like bromine or chlorine in the presence of either light or heat to give you alkyl halide, in this case alkyl bromide. So this will be bromoethane or ethyl bromide. That is a free radical reaction. So free radical reaction requires an alkane, a halogen X2, and then either light or heat. So light, sometimes they use this, and then heat, sometimes they use that triangle to signify heat. And this mechanism has 3 steps. Even without being told, you just have to know that free radical reaction has 3 steps. Step number 1 is initiation. So that is what starts the whole process. Step number 2 is propagation. And this is what keeps the reaction going. And then step number 3 is termination. This is what kills the reaction. Initiation. So for initiation, you start with the halogen. In this case, we have bromine. And then here they say you use light. So with light, you end up breaking that bromine, but that's going to be what we call homolytic cleavage. That means the bond break uniformly. So remember, the bond here has 2 electrons. 1 electron moves to this bromine. You use half-headed arrow because it's a single electron movement, and you end up with the product Br dot. So you end up with bromine radicals, or you could just say twice bromine radical. For step number 2, you bring the bromine radical that was formed in the first step, and then that will react with the ethane that we have here. So CH3CH3, and I'm going to rewrite that as HCH2, which is CH3CH3. The reason I want to show this bond, HC bond, is because I'm going to break it in the course of this reaction. And because it's a single electron process, the bromine or bromide radical will form a bond with that hydrogen, and the hydrogen will break also. You get 1 electron flowing to form a bond with the bromine. At the same time, the hydrogen-carbon bond breaks, and then the other electron that's left flows to the other carbon. And this will give you this product, HBr, and that's from these 2 here connecting. And then plus, here we're left with CH2, CH3, but now, see here, 1 electron moved to the carbon, so you have a radical there. So what happens with a propagation reaction is that you end up using 1 radical, 1 neutral species, and then you end up generating a neutral species and another radical. And then in theory, that radical will continue to react. So it keeps on going. You're always generating a radical in the propagation step. The termination step is what kills this reaction. Remember, this reaction is driven by radicals, and therefore the termination step will involve the radicals coming together. And if you look at what we have several possibilities. We have Br radical, and we have CH2CH3 radical. So we're going to use those for the termination step. The first one will be the Br dot reacting with another Br dot or radical. And again, you use 1 half-headed arrow, and you end up with a Br bond. So that kills the reaction because now you've quenched the radical. Or you could have the CH3CH2, I just flipped that, plus CH2CH3, that's the same thing, radical. And again, use 1 half-headed arrow, and you end up with CH3CH2, and then you form a new bond, and that becomes CH2CH3. And then lastly, you could have the bromine radical now reacting with the ethyl radical, again, 1 half-headed arrows, and you end up with the bromine forming a bond with the CH2, CH3. And that will be the full mechanism for that reaction. Thank you very much for your time. Please support the channel by subscribing and also by liking the videos and commenting on the videos. See you next time.